Thank you. Can you hear now? Yes. So, and I'm happy to talk about something which is probably a bit less technical than what we heard before, but to me has been very, very exciting in doing. I start with the credits, just not to forget. What I'm going to tell you about today comes out from an European project called Amadeus. Also, there is a book which describes part of this work, including the talk I'm giving today, is freely downloadable. So the electronic version is completely open source. And last but not least, I enjoyed a lot doing these things together with Herman Kopetz. Emergence. Emergence is not a new topic. You see, it dates back from some years. Emergence states that the whole is greater than the sum of the parts. And this was already said by this guy, Aristotle, long ago. And emergent phenomena come about the interactions of the part. So for us, emergence is not something that you must be surprised because you don't know, because otherwise, say, depending on the viewer or the observer, you would not have emergent behavior. But emergence is something which you cannot trace to the part, even if you know very well how to provoke it or that it will happen, as many things also in computer science that I will show you later. And you see here, the whole is greater than the sum of the parts. For us, the whole is a cyber-physical system of systems, so the union of several systems which have also a physical part, and the parts are these. Say, it's probably a new name for embedded systems. It's up to you to say. What is for us a system of systems? A system of systems is an integration of a finite number of constituent systems which are independent and operable, so systems which can be operated by themselves, which are networked together for a period of time, so not forever, for what is necessary to achieve a certain higher level goal. So something which cannot be achieved by any of the constituent systems by themselves. And the constituent system is, again, an autonomous subsystem consisting of a computer system, possibly a controlled object with physical parts, and maybe humans. So myself driving an automated car am a constituent system of a possible systems of systems. So here you have the ATM, but the entire network of the ATM is doing more than the ATM of your banks, because you can take money whenever you are, in which currency is the local one, and so on. Okay. So they communicate during this amount of time they are connected. And if we see a constituent system very roughly structured in this way, we have a human, and we may have information flowing through, let's say, relied upon human interfaces. Then we have a cyber part in which you have all the messages Marco was talking about, in which you have relied upon message interfaces. But then you have also a physical part. And also here you can have information flowing around through stigmergic channels, what we call stigmergic channels, and we have relied upon physical interfaces. When I'm driving and I turn on the blinking left light, what am I doing? I'm trying to convey an information which is through a physical environment, and the driver behind me, usually because of convention, understand that my intention will be to turn. So we have also very clear examples of flow of information which happen through the physical world. And many of our cyber physical systems have interactions in which information is let's say, loops of information are closed through this physical mean. Not only, physical systems are controlled by laws of physics, and they have a dense physical time. They obey a dense physical time, while let's say a cyber systems is controlled by program execution, governed by the execution time, and normally the time base is sparse. You have instances where you do things, and you have clocks which are discrete. And a cyber physical system has to harmonize these two worlds and has to take physical information, bring here with digitalization and conversion, and then be able to build its, let's say, actions or decide its actions according to this, maybe deciding whether it wants to communicate by messages or through the physical world again. Then let's come to the real motivation of all our investigation, which is essentially to reduce cost, because today in let's say the specification, design, operation, and evolution of large system is in the non-physical domain. And the cost of all the hardware and what is around is much, much less and is modest with respect to the engineering effort that we have to imagine, design, build, control these kind of systems. And the engineering effort depends on the cognitive complexity, the degree of cognitive complexity that we need to understand the behavior of a system. I mean, big and complex systems are becoming so complex that we are not able to master them, or in general, there is a complexity explosion which makes them very hard to build and very hard to control. And then they may be also very dangerous because they do things that we are not able to control. So any reduction in this is of very huge economic importance. Our ability or capacity to understand systems. What is exactly cognitive complexity? We have several types of complexity. Some view is that complexity is a property because it's structural, dynamic, but actually, is it a property of an object or of something, or is more a relation? We believe that complexity is a relation between a scenario and the system and an observer. For me, something may be very complex. For some people skilled in a given topic, may be very simple. If you ask me things that are outside my competence, no way. So the same thing can be more or less complex depending on who is the observer. And if we do this, we should understand that this becomes very, very important, especially in many new, let's say, applications field that we are attacking now. Self-driving car, is one of the main examples. So cognitive complexity is the question, how much mental effort is required in order to understand a given scenario for a given purpose for an identified user. So I have a user, a purpose, and a scenario. So I need to take, let's say, representative of a group, set of engineers, for example, and so the effort and the time necessary to understand depends on the skill of the group, the average engineer, the purpose for the understanding of the understanding. Should I analyze something? Should I build something? Should I do something else? The inherent characteristic of the scenario. Clearly, there are systems which are more complex than others by themselves, and also the representation of the scenario. So languages that I can use to make models for my system, which may be or may allow an easier understanding or more difficulties in understanding. I mean, there's a lot of people doing with SysML and UML and all these kind of things, which are really very much concerned with this. So, when I say I understand the behavior of a system, what is really what I mean? Actually, I have a mental model. I can imagine how causal links can be established between the input, the states, and the observable output. I really understand the system when, if I know in which state it is and which are the inputs it's subject to, I can devise or predict what will be the output and the behavior. So, understanding a system means exactly building this mental model. Let's come to a first touch to emergence. Emergence for us is a phenomenon of the whole at the macro level, which is new with respect to the non-relational phenomena of any of the parts. So we have to find emergence when parts interact to each other to produce something new. This is an emergent phenomena of a given group of cars which interact and have some relations among them. And we have different kinds of emergent phenomena. Positive. Yesterday I've been able to get some reais from a teller machine. So there's a system of systems of teller machine in which a service is provided to the users in a way that not any single system can do. And it was designed for that. But also there are detrimental emergence. Blackouts. Normally, independent and uncoordinated access of multiple consumers to a network, to an energy supplier, cause a blackout. Not any single user is to be blamed because any of us turn on their TV, but then when the charge is too much and there is no coordination, it may happen that we have this blackout, or that too many cars together go in some parts and you create let's say a traffic jam. But if we think a bit, is exactly to obtain emergent behavior that we design and we compose systems together. Because if the service we want would be provided by an existing system, no need. So emergence is the essence of what we try to do. Also, Marco, in what he's doing, is trying to get something out of the parts which is better than any one of the parts can provide. So, but we would like to be able to do what? To manage emergent phenomena and master their appearance. So, we would like to govern and manage emergence so to have only the good one. And say, for me, this is particularly important as I come from the world, the safety world, where emergent phenomena can be really catastrophic and very, very dangerous. So, mental model and understanding. We have been looking a bit around and say, in order to understand, we have found that we need proper modeling structure. And in this structure, say, we should limit the complexity of any single item of our structure and be able to integrate a multi-level sort of vision of our system. And the only model we found is that of hierarchies. You have multi-level hierarchies in which each level possesses the proper set of laws, and that can be composed together in order to let us understand. And we can see in the normal world, in any kind of science, that understanding is structured in several abstraction layers. We have details, but then we abstract some and we deal with something else, and so on. And emergence is always concerned with two levels of a hierarchy. And to represent this, someone at some point in philosophy introduced the term holon, that was introduced to refer an entity which is at the same time some parts and the whole. Okay, all and parts. So if we see from a micro level, the holon is a single entity, a whole, but if we see the bottom line, the micro level, we see that there are a lot of interacting parts. Okay, and say interaction are limited inside this world here, and interaction with external can come also only through the upper part. So the parts here are hidden to the rest of the world because at some point the holon behaves as a whole. And if you consider this concept, you can see it in a recursive way. You have parts that form a whole, and then several wholes becomes part of a higher whole, and so on and so on. So this can be, let's say, is a recursive decomposition, and essentially we stop it when we consider further decomposition not necessary for our understanding or not relevant, and we don't have any motivations to split it more. And these systems are the elementary ones. Now, just to give an example of this recursion, say here you can see these as atoms. Atoms are ruled by the laws of physics. They are together and they form molecules. And then some molecules interact to each other. They form complex structure in a given way. But to deal with molecules, we normally use laws of chemistry. So we moved looking at atoms from laws of physics to laws of chemistry. And then we have cells. And we move to biology. And cells together can form organs. And we can talk of medicines. And organs can form humans, for example, or animals. And we move more towards sociology, kind of science or disciplines or laws to explain the behavior of the entities at the proper level. And you can see that, at least in biology and philosophy, this has been a driving force for, I would say, centuries or millennia. Say, we are a very young discipline or science. So we think that sometimes we should also try to learn the way also of thinking and the attitude and the approaches coming from elsewhere. And say, if we take this kind of hierarchy and recursive stuff, we see that we have relationships among the things. We have interaction relationship between entities at the same level which interact, and we have also level relation between one level and the one at the bottom. Okay, and then I'm going to describe a bit of these laws. Level relation. Containment, the whole contains or consists of the parts. Molecular contains atoms. Control, the whole constrains the behavior of the parts. You see, ants, termites, the blinking of fireflies, the group constrains the behavior of the individual. If you see flying ducks, they assume a position which is dictated by the group. So in that sense, the group has some control on the individuals. Or description, the parts can be described at different level. And also, these relations may not be exclusive. Okay. Clearly, if we want to analyze the behavior of our system, let's say, the control hierarchy is the most relevant and interesting. Okay, and essentially we have that on one side, the whole constrains some degree of freedom from the parts. The parts are, how to say, constrained. They are not completely free to act because of the whole. And on the other side, we need to allow some degree of freedom to this part. So we observe in several cases some equilibrium, or there is equilibrium between how the whole constrains the part and how the parts are free to move. And this interaction is in some cases very interesting. For example, here you have the players, which are the parts, and you have the conductor, which is constraining the behavior of these parts. I mean, this is an orchestra. You can see it as a whole, as an orchestra, and you have the whole which is constraining, still leaving some freedom to the different musicians. And we have other examples. Essentially, we have two different forms of control of the whole on the parts. There is an authority from the outside, for example, a general over the soldier or the conductor over the orchestra, but there is also authority from the inside. The union, the ensemble of the parts at the macro level controls the individual on the micro level. So the higher level is equipped with causal powers on its own that can limit the lower level and the behavior of the different part. So from the point of view of emergence, the authority from the inside is by far the most interesting. Then we have interactions. We have interactions which at some low level can be force field, okay, magnetic or gravitational, and these are independent on time. Then we have information relations or interactions. They come about the exchange of information items, as I explained before, can be through messages at the cyber part or through the physical environment, but still they are information. And they are instead diachronic. So they develop along time, and here time becomes an important factor. Emergent behavior in system of system is caused by these information interactions. Physical interaction, okay, we have, but they are not relevant in our talk. Information interaction. Which kind of information interaction we can have? It's direct information, event messages or state messages, if you talk about control system, that can be queues, they can be state message, can be idempotent. We have also indirect information, which are file-based or publish, subscribe. So we have messages in the cyber world, and we have indirect information through physical channels, say the blinking of a light or the pheromone of the ants when they find the prey, and then they set the path for the other one. And we have physical space, which is another place where information can take place. At this point, I can really properly define emergence. Okay, for us, the essence of the occurrence of emergent phenomena lies in the organization and the relations of the parts and the interaction, physical or informational, among them at the micro level. So a phenomenon of the whole at the macro level is emergent if and only if it is of a new kind with respect to the non-relational phenomena of the proper parts at the micro level. So again, I stress the concept is novelty, not surprise. It must be of a different quality with respect to what we already know about the parts. It's not because it's the first time that we see something that it must be emergent. This is not a definition that we can accept. And emergence is a very powerful simplifier, if you think the concept, because it is thanks to this emergent phenomena that we can lead to simplification of the world and to understanding of the world. Say, this is an example that all of us should quickly and easily understand. A fault-tolerant distributed clock synchronization. We have a group of clocks. We can organize and let's say, in a fault-tolerant way, a synchronization of the clock, and we have at that point a new abstraction, which is the notion of global time. Okay. Or interaction of transistors creates a whole that can be described by the law of the Boolean logic instead of the old laws of the transistors. Or a multitude of atoms of gas leads a new whole that is characterized by the new concept of pressure. Okay, so these are example one. This is from electronics. This is from a different topic, but this should be quite interesting to us. We take some parts, some processes, we are able to structure their collective behavior in a way that we build a different abstraction. And from then on, we can assume that in our system, we have the distributed global time service and notion available. No need to think how the algorithm for clock synchronization is designed or implemented. Simply, we can reason at a different abstraction level. So we need very often new concept at the macro level to explain what is the new world that we have found. Liquidity, hydrodynamical laws. So we have these bridge laws normally whenever we have found them, because for not all the phenomena we know, that relate the concept of the micro level to the concept of this new macro level. This is not really the main part. We also have this concept of downward causation, which is exactly, let's say, the very reason of emergence. The parts, the interaction of the parts at the micro level cause the whole, and the whole can constrain the behavior of the part. So we have very often causal loops. The parts constrain the whole constrains the part and create an equilibrium, which is, let's say, the origin of emergent behavior. Because the way the two interact give exactly rise to this. Linear causation cannot be the reason of any emergent behavior, because the part would dictate what the whole would do. So here we have this, as I said, equilibrium. On here we have the whole which is constraining the part. Here we may have other forces like the laws of physics or other imposed laws which tells us how entities have to go together on the micro level. And here we have a small free behavior of the part. This free behavior of the part in correct systems is the degree of freedom of the different setup which still provide the same service. Okay. let me move on. Last, to conclude this, let's say, more philosophical part before coming to the technical, is supervenience. Actually, we have two very important concepts at this point of supervenience. Supervenience one says that a given emerging phenomenon at the macro level can emerge out of many different arrangements of or interaction on the part of the micro level, which means that very different setups or very different arrangements can originate the same behavior. And as long as they do, I mean, we are fine and we don't need to know the specific and detailed stuff. Supervenience 2 says that the difference in the emerging phenomena at the macro level requires a difference in the arrangement or the interaction of the parts of the micro level. Means that if I observe something different at the macro level, some change must have occurred at the micro level. And this opens the way to things that we do normally. Supervenience 1 leads to simplification. Here, there's a detailed description of the example of the transistor in which the chemical components and the chemical part can behave in many different ways, but as long as their behavior is as designed, then we cannot consider which of the several different configurations we obtained, but we talk about the transistor itself. Supervenience 2, well, when we state that the difference in emerging phenomena at the macro level requires a difference in the interaction of the parts at the micro level, we say that whenever the observed behavior at some level deviates from the expected one, the intended one, there must be determinant at the macro level some cause, some changes, which is the cause of the observed failure. So whenever we observe a failure, there must be in our setup something which changed with respect to before and which is the origin of this, let's say, change. Now let's come to a few, actually I have more, but I selected very few examples of phenomena that are emergent in computing literature. Deadlock, first, fault-tolerant clock synchronization, and then the 2010 stock exchange flash crash, which so far has not been explained. Look at this. This is, say, very simple code. There are two types of processes. They get, say, there are two semaphores, money and seats, try to make a reservation. Okay, and if you check the code of each of these two types of processes, they are perfectly correct. The first tries to get the money, and then, if not, freeze the money. If success, tries to get the seat. If not, release everything. Otherwise, takes the seat and the money and freeze and completes the transaction. Right. The other one does the same thing, but starts from the seat. Getting the seats, checks for the money, and then releases everything. Should be clear, very clear to all of us, I mean, for what we do, that if we instantiate some of these processes, I mean, we mix A and B, and we run a system, we have a chance to get a deadlock, right? Because when a process type A meets a process type B and vice versa, the deadlock is sure. But still, individually, each of these is correct. There's nothing, if I look this code, that can tell me, look, you will have any problem. If I keep in the world of the parts, the lower level, the micro level, things are fine. Then I have several parts in the micro level, they start interacting together, and I have something, in this case, bad. Okay? And you can believe me that the first time people have observed this kind of phenomena, it was quite a surprise, and the explanation and the understanding took some time. So we can understand and we can learn, but maybe the first time that we see something can be a surprise, unexpected. So deadlock is an emergent phenomenon. In the micro level, everything is perfect. The code of any of these processes is correct. The novel phenomena is a permanent halt of the system. No process can progress anymore, which is something we didn't know if we keep the word of the single process. Is it explainable? Well, personally, I fire my students which don't know how to explain a deadlock. I don't know here the rules, how they are, but I don't think they should be much different. We have a downward causation because we have an information transfer via the semaphore variable. So the whole is constraining the single process, and the single process is acting on the whole when they modify this variable. Is it predictable? Well, we can imagine that we can have it, but is not deterministically predictable. We know that we may have the possibility, but there is some indeterminism caused by, let's say, the simultaneity of the different run, which make the deadlock condition proper. But we may be lucky and run some processes of type A and type B and be able to finish the run of the system without finding or encountering a deadlock. So it's not predictable in this sense. It's something that we have there, may happen, but we don't know exactly when and how. How we know, but when and if it will happen in a given run. Fault-tolerant clock synchronization. Okay, let's talk about clock as the object of an agreement, and again we can talk about 3K plus 1 things like exactly in the Byzantine example. Okay, K clock can fail in an arbitrary way without the loss of the global time, because the other clocks will agree on some value, and the notion of global clock will be available for all the participants, which are the correct processes. So we have a novel phenomenon, which is the tolerance of clock failures and the notion of the global time base. Okay. Is it explainable? Yes, very easily, if you are in these kind of things. Downward causation. Well, the time average of the set of clocks inflicts a state correction to a local clock. How can I synchronize? I take some other clock, I make the average or the median or whatever you want, and then I adjust my local clock according to this. So it's the set of the ensemble which is constraining the behavior of the single. And also, we have some upward causation, because each clock physically has a physical oscillator, and you cannot change the physical oscillator. So it's something which comes from behind that you have to account in your clock. So this is exactly an example in which we have the forces from up and forces from down, and you find an agreement. And can we predict it? We designed for it, so we can predict. In this case, as long as K, no more than K clocks will fail, we know algorithms that will allow to build the abstraction of the global time base. And then I can reason on my system just as having for granted this global time. Then, clearly, if a local clock does not work according to the rules, we declare it failed and we expel from the group. And this is okay for us. Stock market. May 6, 2010. Stock market. There were still humans making the orders. Fast ones could react in 1 second to the events. Then we had, let's say, automatic actors, which can be able to react in 1 millisecond. And at some point, this happened. There was a crash, you see, lasted about half an hour, where, let's say, some shares, some stocks went really down and some were really high. A lot of people lost or gained a lot of money. For 8 years, a lot of people have been investigated for that. Let's say operators accused not to have a proper behavior. But clearly, recent studies says that they cannot have caused this by themselves. I mean, if you are a small operator in there, you are not able to induce this kind of thing in order to get money for you. Okay? Say, all the investigation run so far have not been able to explain causally the reason of the thing. Okay? Probably we would need to have a much, finer control over the orders and the actions. It's not clear when, I mean, the timing of the different things is not clear, so it's not easy to see what caused what. If you don't have a global time ordering, you are not able to do this. But anyway, there are still investigations, and this problem has not been solved. And is clearly determined by the interactions between all these systems which are participating to the stock market. So is a group, say, the micro level, which had interactions and the behavior which caused a clear deviation from what could have been a normal, let's say, the expected result of the interaction. Also because there were no reason specific. I have another, this on the back, then I will go. This is what happened just after the Brexit, just after the referendum. You see, this is the pound value, and as soon as the market opened after the referendum, this was the effect. But here you have a reason. You can easily explain, because due to this event, the result of the referendum, most people decided first to sell the pounds and then the thing stabilized. Okay, but in the other case, there's no global reason that can explain this kind of behavior. It was completely surprising, in a sense, and unexpected. And the US, let's say, justice is still trying to prosecute and to investigate if they find someone responsible, provided there is someone or some two responsible. Now, how long do we have? Another 10 minutes, okay? Because now I'll tell you some implication of all of this in when we talk about safety critical systems. Emergent phenomena in safety critical systems. Obviously, we are interested in behavior, safety critical system in bad behaviors, which are unexpected, because when we design safety critical system, anything that we expect not to be very good is by design constrained or eliminated. Explanation. Well, if we look back, most of the times we have been able to explain previous disasters. Okay, so in principle, these things can be explained, even if we would not learn by the explanation of disaster, would like to prevent some of them, and obviously must be of catastrophic effect, because we don't care of slightly negative or positive things. It's a good surprise if they happen, but they are not worrying us. What is worrying is catastrophic. And if I have to make a very rough classification of emergent behavior, I can divide expected and non-expected, which means known and unknown. Now I would classify deadlock here. Is known. I know exactly how it develops and the reason which are at the basis, and I have instruments to build a system in order to mitigate or to avoid the problem. Okay, so what we know normally is not a problem, because we can act here. This is what we design for. The fault-tolerant clock belongs to this stuff. Then here we have the unexpected. Sometimes we have, I don't have any example here, but we have good emergence which was unforeseen, and we are even more happy. We try to get a bonus more from the owner of the system or the boss. But this is our problematic case. The flash clash would stay here, and other things would stay here. We believe that with proper observation and documentation of what the parts do and the system does and the semantics of each participant or component, well, the occurrence can be explained first, and say we can do even something more. What we would like to do is to mitigate or to avoid the detrimental ones. Let's see what are the possible reasons and where to look for. Say, we have these two types of channels where interactions can happen, and we understood that emergence can raise from the interaction of the constituent part. But then, since we have these physical interactions, well, what is the role of the environment? Sometimes the environment is playing to give false information, to prevent correct information to flow, or the environment is used by, say, enemies to get information that we don't want to disclose. So, question is what we should do and how we should constrain the environment. As a person having been worked for years in safety critical systems, I can say that normally when we have this kind of system, people try to limit what the environment impact can be on the system. So they are very defensive in that. But, and again, how can I define and model and understand the behavior of the environment? And this is the first big problem. Clearly, it's about ignorance, because it's something artificial that we do. If we are able to limit the complexity, to trace all the communication, to define exactly the behavior of all the components and so on. But there are many sources of ignorance. Do we know the full set of system behavior at the micro level? I mean, if we talk of open distributed systems, do we really know the behavior of each individual system, maybe some legacy or some COTS component? then this is the list of things for which we are ignorant. Sometimes we design or we see emergent a system of system and requirements are not clear at that point. And if we don't have clear requirement, we start very badly, actually. The behavior of the constituent system, the complete set of interactions among them, along all the channels, say open and covert channels and physical ones, and then the impact of the environment. So this is the list of the things we should loop. On the other side, we have, let's say, we know that a causal loop can develop only if there are cyclic information flow. So we must look for this information flow, both in the direct messages system, the indirect information through files and through publish subscribe models and so on, and through stigmergic channel. But as the scope may not be completely defined, it will be impossible to find all these things, say, beforehand at design time. And this is a fundamental limitation, because if we don't know what the scope is, and we don't know who the actors will be, it is impossible to make a list of all the possible information channels that will be used. What we can work on, and we actually did some work in this direction, is first to have design models that can express all these things in order to build the safety arguments and eliminate a lot of these unwanted emergent behavior at design level. But again, this design model may not take into account emergent effect that cause a deviation because new actors come in, new requirements are there, or failures, strange failure semantics of the components. So the defense at this level is observing or considering that this emergent behavior develops through time, because all these interactions happens through time and have a time scale. Then we have to try to detect the start of some anomalous behavior that deviates from the intended one. And we developed a lot of anomaly detection or intrusion detection kind of algorithms in order to, let's say, have time or detect early, so that to have time to mitigate the causes and to avoid the real dangerous stuff. The other thing is to find an explanation for anything anomalous that we find in order to get a better understanding. So this is my conclusion. We spoke about emergence. I mean, emergence is, from Aristotle, is there. What does it mean for computer scientists? In doing this work, actually, the part that I enjoyed most was workshops with philosophers. Because most of the talk, if you see, is non-technical, but can really set up a proper scenario and terms and understanding for these things, which is, let's say, something which will be more and more important, because say systems will be more and more integrated together with many things and many interactions, and these interactions may be source of value or damage. Okay, questions? Yes.
Let's talk about the system of systems and compare different systems. So, like TCP IPs, there are multiple levels in the applications. Maybe the UDP and the TCP, for example, maybe is one or and two systems in my applications. So, does that system defined is just based on this levels of point of views, or just have other kind of things that can define such kind of systems?
Well, I confess I didn't get
So
the question.
what's your viewpoint of define the systems in the system of systems? What does this have some baseline?
It's asking if when you define systems of systems, what's your baseline? How
to define the system?
how to define the system?
It's called a computer as a system or called a screen as a system.
I mean, it depends on the abstraction level you put yourself. Say, if I must reason about integrated factory, in Europe now we have the Industry 4.0 stuff, which is made of intelligent and mobile machinery which together cooperate. My first level is these machines and their cooperation. But then obviously if I look at a single machine, I can decompose it as if it was a system of systems. Take the traffic. I show the different traffic jam pictures. If you take as your system of systems, I mean, the entire traffic, namely the cars and the traffic lights and all the ground equipment that you have a level. And in that case, the car is one constituent system. Then, if you look and you are interested in exploding the car, you can see that the car itself is a system of systems in which you have several subsystems or components. So, as I tried to say, the level of the compositions depends on your interest and on the kind of study or understanding or actions you are planning to do. You can go even higher, or say transport. I have road transport, but I can also try to understand what would be integrated transport when you put also metros or tram lines or buses or trains. And then each of these components will be a component of these systems, still being a very complex and huge system of its own. So you should see it as a recursive kind of concept, and you should position yourself in the levels you
So this is bottom up design. So I define the systems and I got the system of systems.
But what is a system for you?
So
I try to define a constituent system as an independent system which is operated. And I said I can decompose this up to the level in which I'm no more interested in decomposing, and I consider this an atomic system. So for you, it could be atomic a car or one component within the car.
so it depends on what levels you see this.
Exactly. And the powerful of this way of reasoning is that you can apply it at several different levels. Say in the world you want to act on.
One more question. I have a question.
Yes.
Because of course, it's a good, an interesting point of view, because with the more cyber physical systems you have deployed, these kind of things, of course, will happen, unpredictable things. And how do you relate this kind of view to the autonomic systems view, where you have this kind of self-star properties and try to somehow formalize this, what you should do when you don't predict everything in order to control things? Do you have any opinion about this?
The autonomic world came out when people were trying to find automatic solutions in the systems themselves to react to some or to provide some property. Okay. It was automatic in the system. Here, we are not saying that for us, in a given context, a human is a constituent system. itself, and that you can have intelligence and so on. So the system must be able to evolve, but does not necessarily own all the responses like autonomic system. Then you can also say that what you do in an autonomic system, that you provide some higher capability, can be mapped exactly in this kind of concepts. If you design for having self-healing systems, then your design will be tailored for that, aiming at that, and this will be your emergent property. But in any case, these properties that they were finding could be obtained only through the interactions of several components, and obviously were more, because otherwise they would have had a single component which was able to provide all this service for the rest, while it was a cooperative kind of stuff. So in my view, this kind of work we try to do, especially going into this new world of interconnecting physical stuff, IoTs, and so on, includes conceptually the autonomic vision.
Andrea, thank you very much for the nice
Ready
talk.
for the coffee?